Hi, everyone. My name is Nandan Tammineedi. I'm a tech lead at Ascend.io. I'm here to talk to you today about the Ascend platform and the future of data automation. So here's the agenda for my talk today. I will be providing an overview of the Ascend platform. I will be talking a little bit about the capabilities of the platform and the architecture behind it. And then I'll move over to talking about how this architecture has evolved over the last 2 years with a special focus on our support for multiple data planes. And then I will end the talk with looking ahead to some future directions for the product. So let's start with a brief overview of the Ascend platform. So Ascend is a fully managed data engineering platform. Users of the platform can ingest almost any kind of data, whether it's immutable event data captured by a server, transaction logs, or operational data from a primary data store, like a MySQL or a Postgres. You can ingest data from also a wide variety of types of sources, like object stores like S3 or GCS, from data warehouses like Snowflake or BigQuery or Redshift, traditional databases again like Postgres or MySQL, APIs like Salesforce, or even streaming services like Kinesis. Once the data is ingested, our platform gives you the ability to transform this data. And this is typically done in one of several programming languages. So users have the ability to write their code in SQL, Python, or Scala. And the types of use cases that these transforms address are really wide-ranging, right? So you have ETL style, extract and clean. You have enriching of data. You have joining of data between different data sources. You have aggregations, roll-ups, and sessionization of events, and so on. Once this data is transformed, data can be delivered to the destination of your choice, right? So once again, you can write this data out to a warehouse like Redshift, or to an object store like S3. It could be a data lake backed by S3 like Lake Formation, or a traditional database. And this list of destinations is growing fast. So we just recently added a write connector for Google Sheets. So as you can imagine, this list is growing. And finally, data can also be consumed through standard analytics tools like Tableau and Looker. So how users will typically do this is they will deliver their data to a Redshift or a BigQuery, and then they will hook up these analytics tools to these warehouses, and in order to power their reports and their analytics. But you can also connect these tools to the outputs of the transforms, right? Which are which form the middle of these pipelines through either standard JDBC or ODBC interfaces. The key point to note here is that the entire data pipeline workflow is expressed declaratively, either through the Ascend UI or through the SDK. So if a user does choose to build through the Ascend UI, what you get is a canvas that looks like this. So you might have to squint a little to make out details here, but I'll kind of walk you through what this represents. So users usually organize their graphs into constructs called data flows in Ascend. So an organization will typically have many of these data flows that look like this, right? So on the left side of the graph, what you'll see are the sources of your data. So these are what we call read connectors, and this is where the ingestion happens, right? So these components are typically config-driven. So a config-driven, what I mean by config-driven is it's something that's source specific. So for example, if you're pulling data from S3, then your config will have something like a bucket or a prefix, and you might have other pieces of configuration, like how do you parse this data? Like, is your data JSON formatted or Parquet? And we also have some more advanced options like adaptive aggregation, which is a way to coalesce partitions in the input for the purposes of improved performance. And then downstream of these read connectors, you have one or more transformations, right? So these are typically multi-stage, the way users build them, and they're code-driven. They're written in SQL, Python, or Scala. And this is where all of the cleaning, the transforming, the aggregation, and all of this happens, right? So what you'll see is a multi-stage pipeline, multiple stages of transforms. You'll see many forks and branches. And the transforms themselves, they vary in terms of their shape and their nature, right? So you can imagine that some transforms are processing data incrementally. So as new data gets delivered, imagine that it's time series data, right? So you might see new partitions show up in these as in the outputs of these transforms over time. While other transforms just reflect, their output just reflects the latest state, right? So for transforms, the key point here is the actual scale, right? So for transforms that actually process data incrementally, you can have data arriving out of order. You could have new partitions arrive every minute. It really depends on the time granularity. You can have tens or thousands or even millions of these partitions, right? So scale is a really important factor in consideration here in terms of what platform you choose. And eventually you have your destinations on the right side of the graph. So again, these destinations are things like S3 or a data lake or a warehouse like Redshift. These are also typically config driven. And you can think of these as the sinks for your data, right? This is where you deliver data for your downstream teams to consume, like your machine learning team or your data analysts. We have another way of delivering data, which is called a data feed. So you can think of a data feed, and you'll see that in the top right of the graph. You can think of a data feed as a way to publish a result directly from a transformation. And another data flow, also within the Ascend platform, can consume the results of this data feed. Or if you want, you can consume the results of this data feed through, JDBC and ODBC. So how does one build a platform like this, right? What are the components of a platform like this? As you can imagine, this is fairly standard architecture. We have it can broadly be broken up into a control plane and a data plane, right? So what I'm trying to do in this talk is talk a little bit about the control plane before moving on to aspects of the data plane. So the data plane is, we'll talk briefly about the data plane here. The data plane is just a collection of Spark-based services that actually do the ingestion, right? They actually run the tasks that perform the ingestion, the transformation, and the delivering of data to several destinations. And they're built on fairly standard building blocks that you come to expect in clouds these days, like EKS for Kubernetes, right? To orchestrate your services. You have S3 for persistence, and something like RDS for metadata. And the control plane, if you look at the control plane, it's divided into a number of different responsibilities, right? And we've kind of bucketed them into basic, intermediate, and advanced, based on what you would see in a standard platform versus the more advanced functionality that Ascend provides, right? So when you think about basic functionality, you have things like dependency tracking, right? When you have an upstream component come up to date or get completed, it triggers the downstream component. And this is fairly standard functionality that a lot of even open source tools provide. But as you go higher and higher up the stack and higher up the value chain, you start to get functionality like job deduplication, right? At the kind of scale that we're operating at, you want to make sure that you don't process the same code more than once if you don't have to, right? You want to do incremental processing in a scalable way. You want to profile the data because that feeds into your efficiency, and you also want statistics about your jobs, right? You want data lineage, right? And this is lineage not just at the column level, but you also want to know lineage between partitions of data. So you have fragments of data that each component produces, but you want to know how they got there, right? How they were produced from fragments upstream, fragments of data upstream. What was the chain of processing that led to that being produced? And finally, you have things like security and governance, garbage collection. And garbage collection is an important kind of aspect of declarative systems like this one. So let's dive a little bit deeper into how the automation works and give you a little bit of a flavor of the kinds of challenges, even the most basic challenges that you have to overcome, right? To build a framework like this, correctly. So let's say you have a data flow in mind, right? Here are some questions you want to be asking, right? When do I run my code, right? So the answer for this is, for sources, the answer is fairly standard, right? So you usually have some kind of schedule refresh, right? Unless this is a streaming source where you're polling more frequently or you're pulling data more frequently. But once you pull data in, once you have a new batch of data arriving or the existing data that you have gets refreshed or changes, you want everything downstream to reprocess right away, right? You might want to do this in regular intervals as opposed to do it right away, but very often our users will opt to have the entire downstream pipeline refresh right away. And you want this refresh to happen either when new data arrives or if your code changes, right? Any component in your graph changes. The other question you want to ask is, did I run this code on this piece of data already, this piece of input data, right? So you'd have to ask yourself, how would you know this? How would you track this data? Right? What kinds of metadata would you preserve? And when you say, did I run this code already? Is that parameterized? What if your input data had multiple partitions, right? And so the same code had to operate on each of those partitions. Do I need to run it again, right? So this is just tied to the earlier question of how you keep track of whether you ran a particular piece of code. Did any of this data change? So is it one of the interesting consequences of a platform like this or certain use cases is your code might change, but sometimes despite the code changing and the upstream data changing, the output of a component might not actually change. And you might not be able to determine this ahead of time, but you do want to make sure that once you produce the same data as you did before, you don't want to trigger downstream processing all over again. Because downstream components are already up to date with respect to that partition of data. So can your framework actually handle that? Right? Did any of the code change? And once the data was generated, you want to know how this data is consumed downstream. Right? So you want to know which components downstream are going to operate on this data, which partitions. For example, your downstream component could just be applying a filter that's just looking at certain old partitions of data, for example, which never change. In which case, that downstream component would never refresh, even if you had new partitions show up in your upstream components. So I think what I'm hoping to impress with the audience here is there's a lot of state management and metadata tracking to consider well before you even go into any considerations of scale or even SLA. So when you start to pull at these threads, some requirements for control planes start to emerge, right? So the core requirement for a control plane is what we call data awareness, right? Which is you have a platform that's aware of all the fragments of data or all partitions of data that were generated for all time, their profile, right? All the statistics of their columns, things like that, where that partition of data came from, right? How it got there. And this is the lineage aspect of it. How it went, how it was consumed. So you're essentially, that there's a large amount of state tracking going on. You want it to be autonomous, which means that you're continuously watching for changes in your code and data. And you're going to be able to scale to trillions of records and more importantly, billions of data partitions, because that really affects how much metadata that you have to store. So I hope you're starting to see a picture where it's more than just triggering jobs on a schedule, right? An advanced data orchestration platform does a lot more than that. So what does it mean to be data aware, right? So at the heart of this data awareness in our system, there's a core collection of metadata tables that tracks a handful of things, right? But the more important entities here are the components, right? This is what the user defines, right, declaratively in their graph. And this is usually configuration or code. And it is not specific to time, right? It is just a definition of what should run or what should happen, right? And then you have partitions that are produced when you run these components. When you evaluate these components and run tasks on their behalf, you produce partitions. You have fragments, which you can think of as partitions, but applied to a storage container, right? So depending on where you're writing it. And then you have the actual tasks, so the jobs that produce this data. So once you have all this data, the job of the control plane is to continuously evaluate the end state that you're trying to get to for each of these components in the graph, and whether or not it actually matches the current state of the system, right? And if not, what you will do is the control plane will generate tasks to drive the system towards that end state. So as you can imagine, this results in, this pulls in all of the characteristics of the control plane that we talked about before, right? So you have the awareness, you have the autonomous nature of it, and the continuously running nature of it. And there's also the declarative aspect of it. As you can imagine, in a system like this, that end state might be something that requires that certain fragments or chunks that exist right now go away, right? So there's a big aspect of garbage collection going on as well. So now that we've talked about the benefits and the features of the control plane, I'd like to change tracks a little bit and talk about some of the recent architectural improvements in the Ascend data plane. So going back even a couple of years, we offered a single flavor of data plane. So we had, in terms of the architecture, we had a collection of data plane services that were built around standard building blocks in like AWS or and other clouds. Primarily Kubernetes, with EKS, some amount of persistence with the blob stores, and also a MySQL instance for metadata. And our transform processing engine was almost exclusively Spark-based. And so the languages that people used to express transforms was either SQL or PySpark or Scala, right? And they were limited to those choices. And the Spark we continue to offer, but we have our own Spark offering. So we're able to spin up jobs as necessary and scale them up based on the requirements of tasks. Here's a different way of looking at this this kind of layered architecture, right? So you have a single flavor of data plane, and you have Spark serving as the compute engine. This is Ascend's Kate's managed Spark offering, and an object store like S3 serving as the persistence layer. And on top of that, you have the control plane that we've talked about earlier. Fast forward a few months, we built integrations with other Spark Spark offerings, like Databricks, right? So we realized that we can keep the flavor of compute engine the same, but switch out the provider and say, it doesn't have to be Ascend's Spark offering, right? We had a lot of users come to us and say, we already have a Databricks account. Can we use that Databricks, right, to run tasks in our data flows? And so we actually started to provide integrations to Databricks and other managed Spark offerings without any significant change in the overall architecture. The key shift in our architecture came with the offering of what we call flex code connectors, right? So this was a redesign of the connector framework to make building of connectors a lot easier than before. Previously, we had a control plane be aware of some aspects of these different connector types, but we made it a lot more modular, and we factored out some of the interfaces that go into building connectors. To the point where now, with the new connector API, we can build new connectors usually in the order of days. So as we build these connectors, we start to see a few kind of overlaps, right? So the connectors mainly addressed the two ends of the graph that I showed you before. You have the read connectors and the write connectors, right? But as we started to build out these connectors, we saw some overlap between the types of technologies we were connecting to and the technologies we were using for transformation. In our case, it happened to be Spark, but we were hearing from numerous data engineering teams that they were using more than one technology, or they wanted to standardize on something different, like a warehouse. And most warehouses offer you the same sort of capabilities that you can see in Spark, or at least there's a big overlap, right? And this also coincided with some of the larger trends that we were starting to observe in the industry. So I think what we were witnessing during this time is also like tremendous innovation in the data industry. And this is primarily driven by competition within warehouse vendors and also between warehouse and lake vendors, data lake vendors. And they were all competing with each other, and they continue to compete with each other to be the primary repository for your data. And despite technical differences between lakes and warehouses, and we know we all understand a lot of these differences, structured versus unstructured, cost versus performance trade-offs, types of use cases, analytics versus operational use cases, access patterns. In reality, there's actually an increasing overlap between data lakes and data warehouses. There's a lot of convergence. So it's no surprise that all of the popular warehouses and lake technologies today offer multiple ways of ingesting data into their platforms, right? And this has also resulted in a standardization of interfaces, right? So, so for example, if you look at AWS, there's lake formation, which can be like a single repository for all of your lake data, for both structured and unstructured data. And you have standard SQL-based interfaces to this data. You can use Spark connectors to pull data out into a data frame, and then you can analyze that in a notebook. There's also even even features like cataloging and data discovery are becoming more standardized and more accessible to our users. And then, of course, there's centralized security and access control. And in terms of orchestration for jobs itself to process this data, you're starting to see offerings like Glue, which take away the pain of having to figure out how to run and maintain Spark jobs and clusters. So in the context of these changes, we had to rethink what a data plane means from the perspective of our platform. So we've come to recognize as these cloud offerings get more and more sophisticated, the catalogs, the warehouse engine, the lake platforms, our users really want the benefit of actually using these platforms. They want to standardize on these platforms, but they also want all of the benefits that come with the Ascent platform, right? The contextual awareness between all of the components, the awareness of what these components do, lineage tracking between the different partitions of data, and frankly, just the sheer productivity that comes with building with the Ascent platform. If you talk to any of our users, they talk about building out their use cases in the time to value has significantly shrunk. And what's more, they have like a single pane of glass to actually manage all of these operations. So we're increasingly moving in a direction where you see something that looks like this, right? So you have multiple data planes in a single environment where data engineers can actually pick and choose within limits, of course. But we're very close to delivering this vision where you can have more than one kind of data plane. We're already offering environments with where you have a choice of data plane offering, but we're increasingly moving in a direction where you can have multiple data planes in a single environment, right? And you can pick and choose. So a data plane, you could have, for example, Glue that's orchestrating your compute jobs, but you could have lake formation serve as your backing storage, or you could pick a data plane that has our Spark offering, if that suits your needs better. Or you could pick a warehouse as your engine for both storage and compute. So your choice of compute and storage platform should no longer prevent you from using the Ascent platform, and that's our goal. And we're within striking distance of this multi-data plane environment. So that raises a question of what is a data plane, right? We've been talking informally about it. So just to briefly cover what a data plane is, it is one or more compute engine. So a single data plane could have more than one compute engine. You might want Spark to process data. You might want the ability to run PySpark or Spark SQL, but you might want a different storage layer. You might not want to store that data in S3, right? So you might want to put that in Redshift, for example. So a data plane is a combination of one or more compute engines in the compute layer and one storage layer, right? Which could be blob store, it could be a data lake, it could be a warehouse, right? Like Redshift or Snowflake. And the important thing is a data plane aligns with, it acts as an isolation boundary for security. So there's no sharing of databases or buckets between data planes. There's no deduplication. So some of the benefits of our platform involve, deduplicating jobs, right, between components. But you won't get that benefit between data planes, and that makes sense. So that there's also no sharing of compute or persistence between data planes in a manner that would compromise security, right? And that's a desirable property of a data plane. So what does a data plane architecture look like, right? So here's a rough architectural diagram. You can think of it as built in layers. So at the bottom layer, you have lower level APIs for compute and storage. So on the storage side, a lot of those boxes will be recognizable from an earlier slide we did about the connector API. So you can really think of this storage API as being almost synonymous with the connector API we already have. So it essentially involves listing assets, listing objects in a data store, testing connections, writing partitions, reading records and things like that. On the compute side, your offering will very often have some sort of jobs API, and it'll give you things like metering. Right? It'll tell you about usage. And built on top of that, you've got to have services like garbage collection, snapshotting, right? Because your system is constantly changing, and so you're constantly, as new waves of batches of data arrive in your sources, you will have new snapshots being produced in each of the components in your graph, right? So you want to have that ability to snapshot and time travel. You have data migration, so you might not choose to rename components. For example, you might want your data to move around. You have job profiling and statistics, right? So this kind of forms a base layer for the API that we provide on top, which is the data plane API, right? Which provides fairly standard, what you would come to expect from a platform like ours. So you have ingestion, transformation, writes, interactively query data. The equivalent of this is, for example, an Athena, for example, right? So if your platform was S3, you could be using Athena. Our query interface would drive Athena, would essentially be using Athena for doing the query. You have schema inference, right? This is a critical part of our platform to make sure that components that are chained together are actually compatible with each other. And you also have resource management, right? How do you model resources for each of these different data planes? And how do you measure usage and cost of jobs? And then you're also collecting usage metrics constantly, right? For purposes of billing. So here are some challenges that we've run into as we build out this new data plane architecture, especially the multi-data plane architecture. So one of the aspects that's challenging is native support for data types varies by platform. And this is not a comprehensive list. This is just maybe the main 3 or 4 challenges we've run into. So native support for data types kind of varies by platform. You have some platforms that don't support integer types. They just do long, for example, right? The ascend schema, the schema that we present to users, tends to be much more fine-grained and have support for a very wide range of data types. But since we're now conforming to these platforms, we have to change how these data types are presented, right, to be compatible. There are also some there's also support for things like in-place updates for some of these platforms, right? So a classic example of this is the SQL merge statement that both, I believe, Snowflake offers and other warehouses as well. And the idea here is you can do efficient in-place updates to a warehouse. And this conflicts a little bit with the way that data engineering platforms often work, which is they expect mutable outputs that you never change. You always copy when you make a change. So we have to support things like this, right? Because when you adopt a warehouse as your platform, you want to be able to get these benefits, but you still want the declarative view of your components in the platform. And there's also been a shift from content addressable to semantic storage. So previously, when we had a single data plane, we were storing the intermediate artifacts from transformations by content. So essentially, we had UUIDs to represent this data. You had to go through JDBC or ODBC indirectly to actually get data for each one of these tables. But now that we're storing data directly in a warehouse, for example, if you choose a warehouse as your data plane, we have to bridge the gap between content addressable and what we call semantic storage. So semantic storage in this case is that the data is stored in a table that has a name and a namespace that more closely reflects how you created that component in your data flow. So your table name might reflect the component name. Your namespace might reflect, for example, your database or your schema might reflect, what data service or data flow you used in the SN graph. So that's what we call semantic storage, and one of the challenges is to actually bridge this gap between content addressable and semantic storage. I'd like to close by listing some of the benefits of a multi-data plane architecture. So one of the benefits is you get true isolation, right, all the way down to the infrastructure. You get better resource isolation, better security. The concept of a data plane is more closely aligned with how people think about a data platform, right? The offerings that you get from a cloud vendor. A single data plane could have multiple compute engines. So for example, you could have Redshift and Spark for your compute, and you can use Redshift for storage. And when combined with the SN product, it really allows you to build, you get a single integrated experience, right, for managing all of these different data products. You get the ease of use of the SN product, but you can also build data projects more along the lines of use cases, rather than the artificial constraints that, of technology and skill sets, which often lead to silos in engineering organizations. So these are some of the benefits that you get when you have a multi-data plane architecture. And with that, it's time for Q&A. Thank you all for listening to me, and I'm happy to take questions.